Hello and welcome in this second lecture of the Introduction to Artificial Intelligence and Machine Learning for Engineers class. So in this second lecture, what we are going to talk about is to focus on problem solving and search. So last time we said that artificial intelligence is the art or the science of getting computers to learn how to perform a given task, a task that typically would require some intelligence. So a task that is typically performed by human, how can we train computers to accomplish such tasks? And so now we're going to start to see some few examples of typical artificial intelligence problems and what are strategies to formalize those problems and how to solve them using computer. The key thing that you should understand at this point is that if a human is approaching a given problem, humans are going to usually try to solve those problems by using their intelligence, by using their intuition, or by using their previous experience, or by using some logic or some planning. When it comes to artificial intelligence and using computers to solve problems, computers are not intelligent. They don't have the level of intuition or the level of experience or the level of reasoning. They cannot think like humans, which means that what we call artificial intelligence is not really a real intelligence, in the sense that computers cannot be intelligent, strictly speaking. What computers can do is to follow algorithm. They can perform certain types of action, sequential action, do this, then do that. And if they perform some action that are performed in a way that is efficient enough or that is fast enough, then computers can appear to be intelligent, although it's a type of intelligence that is very different from human intelligence. That being said, so what we are going to see now is how to approach certain types of problems that are typical of artificial intelligence, and how would you solve them if you were a computer. Again, remember that computers don't have the level of intuition that humans have, so they have to solve problems in a very logical ways by following some instructions, a series of actions, and that's what we are going to see now, is how to think like a computer to solve typical problems that are relevant to artificial intelligence. Okay, so let's see some examples of AI problems. So typical example of problems that AI can help with is one typical example is playing games. So for example, if you are playing a chess game, and if you don't have anybody else to play, and if you're trying to play against a computer, then the way the computer is playing and the way the computer is choosing which move to make, this is something that is governed by artificial intelligence. So planning which move to take in order to win a given game, this is something that falls under the umbrella of artificial intelligence. The second thing, which is something that probably many of you use every day, is navigation. So if you have a goal which is to go from point A to point B, and you want to find the shortest route to go from point A to point B, or the route that has the less traffic, or if point A and point B are some subway station, you want to find what is the best way to go from station A to station B by minimizing the travel time and minimizing the number of different subway lines that you have to take. This is a navigation problem. So in this case, it's a path finding problem where you have different routes, different possible routes that you can take, and you want to find the most optimal way to go from one point to another point. And then finally, you have a more general class of examples, which is everything that is related to planning and scheduling. So this is when you have a given problem that requires you to make some choices. So if you want to solve a given problem and you can make a certain types of number of actions to solve these problems, then the question is, which action should I take in which order, and what is the most efficient way to solve my problem by minimizing the number of actions that I'm doing, or by minimizing the cost of my actions. So in this case, you need to choose wisely as possible the action that you are going to take, and that's something that AI can help with. So in all those cases, what AI will yield at the end is to find an optimal sequence of action to solve a given task. So that's one way to summarize what AI can help with, is to find an optimal sequence of actions. So you have different actions that you can take, and the order of the action is the sequence of actions. So AI can help with finding what is the optimal sequence of actions to solve a given task. And so this task can be going from point A to point B, and the action in this case would be, if you are GPS, would be continue straight, turn left, turn right, etc. So you have different choices to make, which is staying on the same street, or turning right to the other street, or turning left to another street. Those are the actions. So whenever you want to solve a given problem, and if you want to solve it with AI, the first thing that you will need is to formalize the problem, to make it, to transform this problem into something that can be solved with AI. And the way to formalize a given problem is to define 4 different elements that will be key to make this problem solvable by a computer. The first thing is you need to formalize what is the goal, what is the objective of the task that you are trying to accomplish. So the objective, if you are playing chess, is to win the game. If you are navigating, the objective is to reach point B as fast or by minimizing the travel distance. Or if you are trying to find an optimal way to solve a given problem, you need to formalize what is the objective, what is the final goal, when do you consider that this problem has been solved. So that's the first thing that you need to make sure you solve, because we need to decide when has the problem been accomplished. So that's when the AI algorithm will stop. Then you have some given actions. So those are the actions that you can take to solve the problem. So those are possible moves. For example, if you want to, if you're trying to navigate from point A to point B, you can take different actions, which is to continue, to turn, or etc. Like different possible actions that you can take, or it can be interacting with your environment, like moving one object from one position to the next. Or if you are playing game, that's going to be one move of the game, like performing one action in the game. Those are the different things that you can do. And according to different problems, there are certain things that you can do and certain things that you cannot do. So you always have some allowable moves, things that you can do, and some moves that are forbidden, things that are either forbidden by the rules. Like if you are playing chess, you have to follow certain rules. You cannot do you cannot move any pieces arbitrarily. You have to make sure you follow the rules of the games. In the same thing, if you are navigating from point A to point B, you have necessarily to follow traffic rules, but also you have to follow streets. You cannot just go directly in a straight line from point A to point B if there is no street. So you have the number of actions that you can take are restricted by the number of allowable choices that are accessible to you. And then you need to figure out what are the different states of your problem. So the state of a problem is what is changing if you are performing one move. So for example, if you are performing one move when you play a game, you will move from one state to another. In the case of a chess game, for example, a given state would be the knowledge of where is the queen, where is all the pieces of the game, etc. So If you are trying to move from point A to point B, the given state in this case will be where are you located. So you can move at different location, different points within the map, and each point within this map correspond to a given state. And if you're trying to perform some actions to solve a given problem, you also need to figure out what are the possible state that your problem can take. So and again, the state, you move from one state to the next when you are performing an action. Or another way to say that is that performing an action will change the state of the problem from one state to the next. You move from one state to the next by performing some actions. So the states are the possible positions that you can take. For example, the possible situations that can be encountered within your given problem, and you can change from one state to the next by performing some actions. And the goal of an AI algorithm is to find what is the most optimal way to perform the right sequence of actions to go from state 1 to state 2 to state 3 to state 4, etc., up to reaching your final objective, which is to accomplish the goal of the problem. So you want to find the optimal sequence of actions to move along different states in order to reach the final goal that you are trying to make. Again, if you're just thinking of this in terms of finding the most optimal route from going from a given initial position to a final position, you have an initial state, which is the point A position at which you are located, maybe your home. Then the different action that you will take will be first continue straight, and then if you do that, you will move to another state, then turn right. So that's an action that will move you to another state. Then turn left. That's another action which will move you to another state, which in this case turns out to be the final state, which means that now you have accomplished the goal of your given task. So those problems can be qualified as search problem or search algorithm, because the goal of the AI algorithm in this case is to search for the optimal sequence of actions. So the list of all the action and the order of all the actions in order to solve and to reach the goal of your problem as efficiently as possible. So it's effectively a search among all the possible states. You start from a given state, an initial state A, and you want to reach state B as efficiently as possible by exploring different possible states that are intermediate states. You cannot go directly from A to B, so you need to explore and to search what is the optimal path by exploring different intermediate states that is going to make it as efficient as possible to go from A to B. So let's see an example of actual problem, so mostly an illustrative problem, to see how we can solve it with AI and start thinking like a computer and not just as a human. So it's a pretty famous problem that probably you have seen before. So the idea is that you have a given river, and on one side of the river you have a given farmer, you have a given dog, and then you have a sheep, and then you have some salad, and then you have a given boat. So in this case, I hope you enjoy my boat. So the goal of this problem in this case is for the farmer to bring the dog, the sheep, and the salad on the other side of the river, but it has to follow certain rules. First, it can take only one item at a time on the boat. And second, the farmer cannot leave the dog and the sheep alone on one bank of the river, because if this is going to be the case, if the dog is left with the sheep without the farmer, then the dog is going to bite the poor sheep. And on the other hand, it cannot leave the sheep and the salad alone together on one side of the bank, because if you do that, then the sheep is going to eat the salad. On the other hand, it's perfectly fine to leave the dog and the salad, because everybody knows that the dogs do not eat salad. So in this case, the question is, how will the farmer bring all those three things on the other side of the bank while avoiding that the dog will bite the sheep and that the sheep will eat the salad? So in this case, if we want to formalize this problem, so you have a given agent. In this case, the agent is the farmer. So the agent is the machine or the human or the entity that can perform the action to solve this problem. So then we need to focus on the goal of the task that needs to be accomplished, which is in this case to bring everything on the other side. So we are going to call this the near side, and this is the far side. So the near side will be called N, and the far side will be called F. And in this case, the goal of this problem is to bring everything. So to bring the dog, the sheep, and the salad to the far side. So that is going to be the goal. So then, in order to achieve this goal, in order to accomplish this objective, you can take a given number of actions. So the agent can execute a given number of actions. In this case, the action that the farmer or the agent can perform is to cross the river with its boats, either alone or with one item. So only one item at a time. Otherwise, the boat would sink. So can only take one item at a time. So whenever the agent is performing such an action, the problem will move from one state to the next. So in this case, the state of the problem is the position of the farmer, the position of the dog, the position of the sheep, and the position of the salad. If you know on which side of the river those four individuals are located, then that defines the state of the problem. So in this case, the way we are going to define those states is by four letters. So, for example, if I write N, 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 it means that the first the agent, which is the farmer, is located on the near side. So N is the near side. Then the second letters will refer to the position of the dog. So the dog will be the second individual. So if the dog is on the near side, I will write a letter N at the second position. And if the dog is on the far side, I will write a letter F at the second position. Then the third letter will refer to the position of the sheep. And then the fourth letter will refer to the position of the salad. So in this case, N, 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 N means that the farmer, the dog, the sheep, and the salad they are all located on the near side. So this is one state. It's an allowable state. There is nothing forbidden about this state, and more than allowable. In this case, it corresponds to the initial state. That's the initial state of the problem. You have all those four things that are located on the near side of the river. Then, on the other hand, so if the farmer is located on the far side, the first letter will now be F. If the dog is located on the far side, also the second letter will be F. If the sheep is located on the far side, the letter will be F. And if the salad is located also on the far side, then the code of this state is going to be F, 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 triple F, quadruple F. So in this case, this is a state that is possible because all those four individuals have now crossed the river. So this corresponds to the final state, or it corresponds to the goal state. That's the state that you're trying to achieve. And your goal in this case is to find how to search from the optimal way to go from the initial state up to the goal state. And for this, you will need to to go through a series of intermediate states because you cannot directly bring those three items directly to the far side. So you will need to take certain types of intermediate states. So for example, let's see an example. So for example, if I define the state Fn, Fn, so this means that the farmer is on the far side. So the farmer has crossed the street, across the river, but the dog is still on the near side. The sheep is on the far side, and the salad is still on the near side. So this is an intermediate state. It's, in this case, an allowable state. Why? Because in this case, we have, on the far sides, we have the farmer and the sheep, which is no problem. And on the near side, we have just the dog left together with the salad. But the dog is not going to eat the salad. So there's nothing wrong with this state. So it's a state that is allowable. Then if I define this state, so the F, N, N, F, so in this case, this is a state where the farmer is on the far side, the dog is on the near side, the sheep is on the near side, and the salad is on the far side. So on the far side, you have the farmer and the salad, which is fine. But the problem here in this case is that on the near side, you have the dog and the sheep. And in this case, the dog is left without the farmer to checking on it. So the dog is going to bite the sheep, which is in this case a forbidden state. So then the goal will be to find among those allowable states, what is the optimal way to go from the initial states up to the goal state with finding the optimal path along those possible allowable states. And to go from one state to the next, you will take certain types of actions. So examples of possible action in this case would be, for example, if you start with N, 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 where everything is on the left side. One possible action is that the farmer is going to cross the river. So the N will turn into an F for the farmer. And maybe the farmer will take on its boat the sheep. So it means that the dog will remain on the near side. The sheep will now move to the far side, and the salad will remain on the near side. So this action is one of the possible actions. So it's a transition from one state to the next. So you have two states. You can find in this case a transition between those two states. It's you can go directly from one state to the next by just taking one item on the boat. So this is in this case a possible move that allows you to jump from one state to the next state. So this is a transition between two states. In general, in artificial intelligence problems, so you can perform certain types of actions. Sometimes not all the actions are created equal. So certain actions sometimes will cost more than some others. Certain action will be more, will cost you more money or will take more effort. For example, if you're trying to go from point A to point B, and if you have different possible streets in order to go from this point A to point B. In this case, it's not the same to take all the routes. In this case, you will want to find what is the shortest route to go from point A to point B. So in this case, it would not be equivalent to take route 1 or route 2 because the distance of those routes is not the same. So sometimes all the actions do not have the same cost. Each action will have a given cost. But in this case, it's exactly the same cost for the farmer to take the dog or to take the sheep or to take the salad. So all of those actions in this case will have the same cost. So the cost of each of those actions doesn't matter in this case. The only thing is that you will want to minimize the number of times that the farmer is going to cross the river. So you want to find what is the most efficient way to bring all those three things to the far side by minimizing the number of times that the farmer has to cross from the near side to the far side or from the far side to the near side. So now let's see how we can solve this problem using a computer. So again, if you are a human, you can approach this problem using your intuition, using your own intelligence, and maybe you can quickly think using your intuition, using your previous experience about what is the most efficient way to achieve this task by moving first the sheep and then moving this, then coming back, etc. So you have some intuition based on the fact that humans are intelligent and can solve problem just by using their intuition and by using their logic, their reasoning. But if you are a computer, the only thing you can do is to the only thing you know is that you have a given initial state and you have a final state, and you have different actions that you can go from one state to the next, and you can move along different intermediate states. So the only thing that the computer can do is to explore what are all the possible states that can be achieved and to find what is the most efficient way to make some transition, to take some actions to move from one state to the next. So if you want to solve this with a computer, what you need to do is to build a tree. The tree is going to be a representation that represents the possible states of your problem and how those states are connected to each other. So that is to say, what are the different transitions that you can have from one state to the next, which are all the possible actions that the agent can take to move from one state to the next. And this is going to be something that looks like a tree because you have some nodes. The nodes are the different states, and then you have some branches that are going to link those nodes together, and the branches will be the different actions, the different transition from different states, the different actions that the agent can take to solve this problem. So in this case, if you want to build the tree of this problem, the first thing is to list all the possible states that you can have for this problem. So the first possible state, which is going to be the initial state, is the n. So this is the initial state where the farmer, the dog, the sheep, and the salad are all on the near side. Then, so let's start first with all the possible states that can be achieved when the farmer is on the near side. So when the farmer is on the near side, you know that one option is that you can have everybody still be on the near side except the salad. If the salad is alone on the far side, it's not a problem. So that's one possible state. The second possible state is to have the NNFN state. This state is also possible. It means that in this case you have the sheep alone on the far side, which it's not problem. No problem with that. It's an allowable state. Then the next step, the next possible state would be the NFNN. In this case, it means that you have the dog that is alone on the far side, which again is no problem. And then the final possible state that you can have is the NFNF. In this case, you have both the dog and the salad alone on the far side, but again, in this case, the dog is not going to eat the salad, so that's a state that is allowable. So those are all the possible states. There is no other possible state. For example, you cannot have the farmer on the near side together with the salad and just the sheep and the dog on the far side, because in this case the sheep would be bitten by the dog, and you cannot also leave on the far side the sheep alone with the salad. In this case, the sheep would eat the salad. So those are all the possible states that are allowable as long as the farmer remains on the near side. And then let's move now to the states that are possible when the farmer goes to the far side. So again, you will have a collection of 5 possible states, which are in this case, the first letter will always be F because now the farmer is on the far side. And now we need to keep track of who is remaining on the near side and to make sure that there is no forbidden configuration there. So the first possible state is that you will have the dog on the near side together with the salad. That is fine. And in this case, the one option is that in this case, the sheep would be on the far side. So in this case, on the near side, you have just the dog alone with the salad, which is an allowable state. Second state is that the dog is still on the near side alone, and you have moved the sheep and the salad to the far side. In this case, it is fine because you have the sheep and the salad on the far side, but the farmer is still here to make sure that the sheep is not eating the salad. So it's also an allowable state. Then next state, it's the FFNF state. In this case, you have the sheep alone on the near side, which is fine. Then you have the FFN state, which in this case means that you have the salad alone on the near side, which is also a situation that is fine. And then you have the last case, which is the FFFF, the quadruple F state, which in this case is the final state, the goal state, because now the farmer, the dog, the sheep, and the salad, they are all on the far side, which is the goal of your problem. This is what you want to achieve. So the goal here is to go from the initial state and to find the most advantageous way to go to the final state, to reach this in as few iterations as possible. So the way to do that for a computer then is to list what are now the possible branches. So here we have started to begin to build the tree. We have the nodes. The nodes are the different states, and now we need to make some connection between those nodes when you can jump from one state to the next. Those are going to be the branches of the tree. So we need to look at, among all those states, how do you which one is possible to go from, what are the possible transition, like from which states, starting from a given state, what are all the possible other states that you can achieve. So let's take a look at this. So the first thing, the first allowable action that you can take is if you start from the state n, where everybody is on the near side, one possible action is that the farmer will go to the far side, and it will bring with him the sheep. Okay, so in this case, you will have the farmer and the sheep that will go to the far side, and in this case, the dog and the salad will remain on the near side. In this case, that's one possible action, and that's actually the only possible action. If you start from the NNNN states, that's the only action that you can take. You cannot, the farmer cannot move with anything else but the sheep, because if it moves with the dog, the sheep is going to eat the salad, and if it moves with the salad, then the dog is going to bite the sheep. So that's the only possible transition that you can have. Then if you start from the NNNF state, the first possible thing is that, so in this case, when you start from NNNF, it means that the farmer, the dog and the sheep are on the near side, and the salad is already on the far side. So in this case, one possible action is to go from this state to the next. It means that in this case, the farmer will cross the river, and it will cross the river with by taking the sheep with it, on the boat. Another option is that rather than taking the sheep, it can take the the dog. So that's one other possible connection. In this case, it will take the dog. So the dog will arrive on the far side together with the salad that was already there. And the sheep, in this case, will remain on the near side. And that's the only two possible action that the agent can take. So then starting from NNFN. So in this case, you start with, on the near side, you have so you have the dog and you have the salad. Then one option that you can take in this case is for the farmer to just cross alone. Okay, so in this case, that's one option. The farmer can just cross alone. Why? Because in this case, there is only on the near side the dog and the salad. So it's okay for the farmer to leave. The dog is not going to eat the salad. So if it's only the farmer crossing alone, then you will go from this state to the FNFN state. In this case, it means that both the dog and the salad will remain on the near side. So the farmer will just have crossed the river alone on its boat. Then a second possible option that you can take is that when the farmer will cross, it can take with it the salad. So in this case, if it takes the salad, you will go from this state to this one. In this case, the farmer moves, the dog stays on the near side, and the salad moves from the near to the far side. So that's a second possible action. The third possible action is that the farmer will move together with the dog. So in this case, you will go there. The farmer will move from the near to the far side. It will bring on the boat the dog that will move from near to far, and the rest is going to stay unchanged. So in this case, the sheep remains on the far side and the salad remains on the near side. Okay, and those are all the possible action that can be taken from this state. So then if you start from NFNN, one option is that the farmer can move on its boat by moving with the salad. So if you move with the salad, you're going to go to this state. One other option is that the farmer will move together with the sheep. In this case, you will move from this state to this state. In this case, the farmer cannot do anything else but those two actions. And then finally, let's start with the NFNF states. The possible thing that you can do in this case is that the farmer will move together with the sheep. So in this case, you would now reach the FFFF final state. And another possible action in this case is that the farmer will just move alone on its boat. So in this case, if it can move alone on its boat, that would be no problem. So in this case, if it moves alone on this boat, you would reach this state. So now we have built the tree. So the tree is the ensemble of all the nodes, which are all the possible allowable states. And we have all the connection, the branches between those nodes. So we have a given tree. And the goal now will be to find what is the most optimal way to go along those trees, to take those trees in order to go from initial state to the final state. And the objective of this, the way you can find the optimal path along those trees, this is going to be by a tree search algorithm. So this is why we are going to talk next about search algorithm. The search algorithm, the goal of those algorithms will be to explore trees like this. So a lot of problems can be modeled like this. They can be modeled as different actions that will change the configuration, that will change the state of the problem. And if you can model a given problem in terms of those a tree like this, where different actions, you are at a given state, and you can take option A, you can take action A, action B, action C. Every time you take one action, it brings you to a new state, and then from each state you have some new actions that becomes possible. This will result in a tree. So just like, for example, many things can be modeled by trees like this. For example, if you play a game, you have a given a number of possible moves that you can make. So every time you have a series of moves, every time you have one move, it corresponds to one action. So it's going to correspond to one branch on the tree. And again, the goal of those tree search algorithm will be to find the most optimal way to go from the initial state to the final state. So which is what we are going to talk in the next video. So now let's just look at, without even knowing in this case how to apply those tree search algorithm, now that we have the tree in front of us, it becomes much easier to solve this problem than if we didn't have the tree. If you are just confronted to this problem, even as a human, it's not that straightforward to find the optimal strategy to move everything else to the far side. But now if we have this tree, it becomes very easy. You start from the initial state. So here you see that you have only one choice. Now it becomes fully apparent. Now you have reached another state. Again, in this case, you have only one possible choice. So it becomes very apparent that what you have to do is now to do this. Now you see that you have two possibilities. So you can go to FNFF, or you can go to FFFN. And here those are two possible solutions to this problem, and both solutions are just fine. Here there is two solutions to this problem. So let's assume that you are going to go towards this state just because it looks like it is closer to the final state. Then from this point you have only one other option, which is now to go to the NN states. Then here you have only one possible action, which is now to go to the FFNF states. And here, so now you have again two options, but here in this case it's very clear that it's not going to be a good idea to go to the NNNF state, but it's actually a much better idea to go towards the NFNF states, because now you just have to do one remaining actions to reach the final state, the FFFF final state, which is the goal of the problem. So in this case, by representing this problem as a tree, it becomes very easy to solve this problem. And in this case, it's straightforward that you can solve this problem by taking 1, 2, 3, 4, 5, 6, and 7 actions. So here, the optimal solution to this problem, the shortest path to solve this problem. So the optimal sequence of actions that you can take is to do 7 moves. So to do 7 times, the farmer will need to cross the street, the river. So there is another solution to this problem, which is actually fully equivalent, is that you would start by the NNN state. You will first cross the river by taking with you the sheep. Then you will go there, and in this case it means that you leave the sheep on the far side, and it's only the farmer alone on its boat that comes back to the near side. And here what you can do is, now instead of going there, that is to say to have the farmer cross again by taking the dog, what you can also do is to have the farmer going by taking the salad. In this case, after that, the farmer will go back to the other side, but the farmer necessarily at this stage needs to go back by taking the sheep with it. Otherwise, if the farmer was to go back from there without taking the sheep, then the sheep would eat the salad. So it has to go back on the near side by taking the sheep. Then it goes back here, In this case, it means that the farmer is recrossing the river by this time taking the dog and leaving the sheep alone on the near side. Then the last thing is that the farmer will cross alone the river by leaving both the dog and the stalad on the far side. And finally, the farmer will cross the river again by taking this time the sheep on its boat. So in this case, that's another solution which is also fully equivalent to the other by it takes only 7 moves. So in this case, you have 2 possible solutions for this problem, and the shortest way is 7 moves. There is some other possible solution, which would be, for example, to go from there to go there, then 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 to go there, go there, go there, go there, go there. So you could loop like for an infinite amount of time if you don't make smart choices. So potentially you could get stuck if you do stupid action. It's possible that you could get stuck and you would never find the final state, or you could reach the final state, but by doing a lot of unnecessary actions, you would waste time or you would waste money. So in this case, the goal of a smart artificial intelligence algorithm will be to find what's the shortest sequence of action that can go from the initial state to the final state. So one of the main hypotheses of when you are solving problem with AI is that you can always decompose problem as a collection of actions like this, of small actions. And even very complex problem can be decomposed into a given tree where you have different actions and each actions will change the state of the problem. And the main hypothesis behind this idea is that even if you take a complex intellectual task, you can always know the detail of this intellectual task well enough that you will be able to simulate it by a computer, by performing a collection of actions. So you can write this like this. You can say that as an hypothesis behind artificial intelligence is that every aspect of learning an intellectual task, so every aspect of learning an intellectual task, which again we said that AI, the goal of AI is to learn how to solve intellectual tasks that would otherwise require a human to be solved. The main hypothesis here is that every aspect of the learning of an intellectual task can be very precisely, can be so precisely described. You can describe this act of learning an intellectual task so precisely that a machine can simulate it. That a machine can simulate this task. The idea is that even if you take a very complex task, you can always break down this task into very small individual actions, very small action that will change the state of the problem. And if you know a task well enough, and if you know it very precisely, that you can break it down into smaller series of small actions, then if you can break down into small action, then you should be able to have a machine simulate this thing. So the idea of this is that if you take intelligence, so what we define as being intelligence as relevant to human, is that it can be broken down into very small steps. So what we think of, if we approach a given problem and we solve it in an intelligent way, the process of solving this problem can be broken down into small steps, into very small steps. Even a very complex problem can be broken down into very small steps. And since even a complex problem, you can break it down into simple steps where you just have different actions, Each step is an action, a possible action, and each action will bring you from one state to the next. Then in this case, it becomes a tree. You have a given possible number of possible states. You can go from one state to the next by moving over one of the branch of the tree. Each node of the tree is one possible state. In this case, if you can model even a very complex problem, can be modeled as a very big complex tree where you have a lot of branches and a lot of possible states. Then if you can model this as a tree, as a collection of small steps, then it can be solved by computer. So intelligence can be broken down into small steps that can be solved by a computer program. So to finish this lecture, let's see another example of how to encode or how to transform a given problem into a tree that can then be solved by an artificial intelligence algorithm. So in this case, we are going to take the example of a game where the goal is to solve the game, or to solve to find what is the most optimal way to achieve a given goal in this game. So in this case, the situation that we are going to be interested in is the Towers of Hanoi game, where the goal of this is that you have three sticks like this. So you have a board like this and three sticks. And along those sticks, you can put some discs. So you have 2 discs, and initially those discs are located on the first stick. So you have one large disc like this that is going to go around the stick. So it's a hollow disc, and you put this disc along the stick. And you have a smaller disc that is initially on top of the large disc. So in this case, this is the initial state, and you want to find the fastest way to go to the final state of this game. In this case, the final state is you still have the same board here with the 3 sticks, and the final state that you want to accomplish to beat the game is now to have the large disc be on the third stick on the other side, and to have the small disc on top of the large disc on the very right stick. So this is going to be, in this case, the final state. And in this case, so the goal, this is the goal of the game. So in this case, the agent will be just the player of the game, who is going to be performing some actions. And in this case, the possible action will be to take one disc and to move it to another stick. So take one disc and move it to another stick. So those are the possible actions. But some of the possible states that you can accomplish for this, some are allowable and some are forbidden. So for example, what is forbidden, what is not allowed, is to put a larger stick on top of a small one. So the allowable possible states is to have either only one disc on each stick, or to have a large disc on top of the small disc. So just like in the initial state, you have the small blue disc that is on top of the large red disc. So this is an allowable state. That's something that is allowed. And then you have some forbidden states, which are states that are not allowed. And in this case, this would be to have a larger disk on top of a small disk. So if you have the large red disk on top of the small blue disk, this would be a state that would not be acceptable, would not be allowed. So this would be a forbidden state. So the goal is to find, in this case, among all the possible intermediate states that you can have, to find the optimal way to go from the initial state to the final state by minimizing the number of actions, the number of times you are moving one disk from one stick to the next. So again, to solve this problem for a computer, you need to build the tree, or another way of calling this is the state diagram. The state diagram is the same as the tree. It's the collection of all the possible states, where each possible state is one node. And then you will you will add the branches. You will create a diagram that links all the possible state. Every time you can move from one state to the next by performing one actions, then those two states will be connected to each other. You will have a branch which will form a tree. So in this case, since it's a simple game, we can write the entire tree of this game. So we will start with the initial state. So you have your board like this with the four sticks, and initially you start with the situation where you have the large disk like this with the small disk on top of it. So starting from this situation, your initial situation, you have to think, what are the possible moves? What are the possible change that you can do? So here, there's only one thing that you can do, which is to pick one disk. And here, in this case, the only disk that you can take is the small blue one. So there's only the only thing that you can do. But you can take this disk and put it on the very right stick, or to put it in the middle. So you have two possible actions here. So it means that you will have two possible branches with two choices that you can make. So the first choice will be to put take the small stick and to put it in the middle. So in this case, you put the small disk like this, or the other choice is to put the small disk on the very right, and in this case, the large disk remains on the very left of the very left stick. So then you need to think about, for example, if we start from this, so let's call it state 0, since it's the first state. This is going to be state 1, state 2. So in this case, starting from state 1, what are the possible options that you can have? So here now you start to have a few different options. The first option is that you can take the small blue disk and you can put it back on top of the large red disks. That's the first option. In that case, it means that you go back to the state 0. You go back to the initial state. So that's probably not a very smart move, but that's nevertheless one of the possible action that you can take. The second thing that you can do is to take this blue disk and to put it on the third stick, to move the small disk here and to move it on the right disk. So if you do that, this is effectively going from state 1 to state 2. You are taking the small disk and you move it to the very right stick. So that's one option. Another option that you can do is to now start moving the very large red disk. So if you do that, it means that you have your three sticks like this. So it means that now the small disk is unchanged, and you have moved the large disk from the very left to the very right. So that's one possible option, one possible move. So that's going to be state number 3. If we go back now to state 2, so again, you have different choices that you can take. You can start moving the small blue disk, and you can put it back on top of the first stick on the left. In that case, you would go back to the state number 0, or you can take this small disk and put it on the second stick. In this case, it means that you move to state 1, or the last possible option that you can have, which is going to be a new state, is to take the large red stick and to move it to the second stick. You take the large disk and you move it to the second stick. For sure, you cannot take the large disk and move it to the third stick, because if you were to do this, then you would put the large red stick on top of the small blue disk, and in this case that would not be allowed. So the only thing that you can do is to move the large red disk from the stick number 1 and to move it towards the stick number 2. Okay, so now let's go back to, that's going to be state 4. So let's go back to the state number 3 and see what are the possible moves that you can take from there. So the first option is that now one thing that you can do is to take the small disk and to move it to the first stick. So that's one thing that you can do. In this case, what you would achieve is that the large disk would remain here, and you would take the small disk and put it on the first stick. So that would bring you to a new state, which is a state that was not achieved before. So that's one option. Another option is to now start moving the small disk again. So in this case, it means that you would have the large disk still on the third stick, and now you would move the small blue disk on top of the large disk on the very right. So this turns out to be the final state that you want to achieve, so this, we're going to write it the state 5. This is going to be state 6. Let's go back to step 4 now, the state 4. So one possible action that you can take from there is to move the small disk. So you can end up with a situation like this, where you take the small disk on the very right and move it on the very left, and in this case it means that the large disk will still be in the middle. So that's one option. It brings you to a state that we have never seen before. And the last possible option is, rather than moving the small disk from the stick number 3 to the stick number 1, you can move it on top of the large disk in the middle. So in this case, you would end up in a situation where you have the large disk that is still in the middle, and you would have moved the small disk from the stick on the very right. You would have moved it to the middle. So this, we are going to call this the state 7. And this is the state 8. Now let's look at those last states. So if you are at state number 5, one thing you can do is to move the small disk, the small blue disk. So that's the only thing you can do. You can only move the small blue disk, because you cannot access the large disk in this case. So you can put this small disk here, you can move it to the middle. In that case, you would go back to state number 3, or you can put it to the first stick. In that case, it means that you are moving to the state number 6, and that's the only two possibilities that you have. If you are at state number 6, what you can do is take this small disk and move it in the middle. In that case, you go to state number 3. Or you can take this small disk and put it on the stick on the very right. In that case, you go to state 5. Or you can take this small disk and move it in the middle. So that would bring you to state 3. The last thing that we haven't talked about is that you can take the large disk on the very right and put it in the middle. You cannot put it on the first stick because you would put the large on top of the small disk. But in this case, if you take the very large disk on the very right and put it in the middle, then you would go to the state 7. And starting from state 7, the last thing that you can do is to go to state 8 by moving the small disk on top of the large disk. So here we have listed all the possible states, and we have listed all the possible branches, all the possible transition from one state to the next. There is no other way to go from one state to another. We have listed all the possible actions that can be taken. So again, this is if you want to solve a given problem by artificial intelligence, you need to transform it into a tree. And now it becomes simple to solve this problem. Why? Because here you have the initial state. You know that your goal is to go there, which is the final state. And now it becomes easy, very obvious to find what is the most efficient way to go from the initial state to the final state, which in this case is going to be to first move the small disk to the middle, then move the large disk to the right, and then put the small disk to the on top of the large disk. So in this case, in only 1, 2, 3 actions, you can solve this problem. So you can find in 3 moves, that's the shortest way, the shortest path to solve this problem. Of course, there is a other solution for this. You can say, I'm going to first move the small disk, and then move the large disk, and then put the small disk on top of the large disk, then move the small disk again to the left, then move the disk to the right, and then put again the small disk on top of the large disk. But if you do that, then it means that you would have solved the problem in 1, 2, 3, 4, 5, 6 moves, which is more than the 3 moves that we just found. So in this case, what we are going to see in the next lecture is if you have a given tree like this with a given initial state and you want to go to a final state, what is the most efficient way for a given artificial intelligence algorithm to find the shortest path to go from through all those branches, and to find the shortest way, the shortest sequence of actions, of moves to go from the initial situation of your problem up to reaching the final state, to accomplish the goal of the problem. So in the next lecture, what we will see is different algorithm on how to achieve this. Some algorithm are very efficient because they are very fast at finding the solution, but sometimes they are not. It's not guaranteed that they will find necessarily the fastest, most efficient way. They will be very fast at going from the initial to the final state, so they will be very fast at solving the problem, but maybe they will not have taken the shortest path to solve this problem. Maybe they will quickly go through there. Or some problems will take longer. Some algorithm will take longer to run, but they will they're guaranteed to give you just the shortest path. So different algorithms have different strength and different drawback, and that's what we're going to see in the next lecture. And that's also what is going to be your first homework for this class, is to implement, to solve a given problem, and to implement a search algorithm to find the optimal sequence of action to solve this given problem.